Welcome to the course on an introduction to information theory. In today's lecture, we are going to talk about parallel Gaussian channel and we are going to talk about what is the capacity of a parallel Gaussian channel, and in case of parallel Gaussian channel, given an average power constraint, how should we allocate power between various channels. This is what we are going to talk about. Initially, we will assume that the noise is independent across various channels, and subsequently we will consider colored noise, and we will do the power allocation for parallel Gaussian channel with colored noise. So, what is a parallel Gaussian channel? So, let us consider k independent Gaussian channels in parallel. So, you can think of it, so basically you have x1, x2, x3, x4, xk, and these are acted by additive noise, let us say z1, z2, z3, z4, zk, and zi's are independent of the input xi, and these noise samples are also independent. Initially we will consider them as independent across all these channels. Then what we get as output is y1, y2, y3, y4, y of k. So, our input is this and our output is this, output of channel is this. So, we are considering k independent Gaussian channel in parallel, and each of them have a common power constraint, which is basically expected value of x1 square plus x2 square, x3 square, xk square, that should be less than equal to p. So, as we said, the output of jth channel is given by xj plus zj, where j goes from 1 to k. Noise is zero mean with variance nj, and this is considered to be independent from channel to channel. Subsequently, when we talk about colored noise, we will assume that channel is not independent, and then we will compute the capacity expression for that as well. So, for the first part, we are assuming that the noise is independent from one channel to another. So, noise N1 is independent of N2, is independent of N3, is independent of Nk. Now, we are interested in finding out the power distribution among various channels such that our channel capacity is maximized. So, we have a common power constraint which is given by this. So, how should we allocate power to x1, x2, x3, xk such that we maximize our channel capacity? This is the problem we are looking at. So, from the definition of channel capacity, we can write channel capacity as maximizing the mutual information between x1, x2, x3, xk and y1, y2, y3, yk, and this maximize over input distribution with this common power constraint, which says expected value of xj square is less than equal to some constraint p. So, as I said, this is how my parallel Gaussian channel looks like. I have these inputs x1, x2, xk, and these are my output y1, y2, yk. The noise samples are independent, denoted by z1, z2, zk. Now, since my noise is independent, so first this is the mutual information between the input of the channel and the output of the channel for the parallel Gaussian channel. Now from the definition of mutual information, I can write this as differential entropy of y1, y2, y3, yk minus differential entropy of y1, y2, yk given x1, x2, x3, xk. Now what are these yi's? Now yi's are xi plus zi, and xi's are independent of zi. So what would be, so given x1, x2, x3, xk, the uncertainty in y1, y2, y3, yk can be written as differential entropy of z1, z2, z3, zk given x1, x2, x3, xk. And what is the differential entropy of z1, z2, z3, zk given x1, x2, x3, xk? Since zi's and xi's are independent, this can be written as uncertainty in z1, z2, z3, zk. And since these noise over these channels, parallel channels, these noise are independent, we can write this joint entropy of z1, z2, z3, zk, we can write this as differential entropy of z1 plus differential entropy of z2 plus differential entropy of zk. This is because zi's are independent. So then what we have is mutual information between x1, x2, x3, xk and y1, y2, y3, yk is given by this expression. Now we can upper bound this joint differential entropy, this joint differential entropy y1, y2, yk using applying chain rule and using the fact that conditioning cannot increase entropy. Using these two facts, we can upper bound this by this. Joint entropy, you can write it in terms using chain rule in terms of sum of conditional entropy, and we know that conditioning cannot increase entropy, so those can be upper bounded by individual yi's, and that's how we are getting this inequality. So if I plug that result here, what I can do is I can write this mutual information between x1, x2, xk and y1, y2, y3, yk as upper bounded by this quantity. Now this can be upper bounded by, so zi, differential entropy of zi, this is basically half log 2 pi e times n, which is noise variance, and differential entropy of yi can be upper bounded by differential entropy of Gaussian distributed random variable with variance given by p. So if you plug that value in here, we can write that mutual information can be upper bounded by this term. Please refer to the previous lecture where we have derived this. So this can be, then mutual information can be upper bounded by this term, where this pi is given by expected value of xi square and there is a common power constraint. The equality is achieved when the input x is Gaussian distributed with mean 0 and variance, basically covariance matrix given by this. This we already know from a result that we have proved in the lecture on differential entropy. So then the problem of optimal power allocation reduces to finding the power allocation that maximizes power subject to the constraint that summation of this Pi is basically equal to P. Now we can solve this using Lagrange multiplier method. So we form the Lagrangian, which is this capacity expression plus lambda times these constraints. Now if we differentiate this Lagrangian with respect to Pi, what we get is this, that Pi should be equal to mu minus Ni. I'll just define what my mu is. Now power must be non-negative, right? So I'm writing this Pi as mu minus Ni plus, where this operator means that this is equal to x if x is greater than equal to 0, otherwise this is 0. And how do I get this value of this nu? The summation of this should add up to my power constraint that I have. So what does, just pay little attention to the power allocation policy that we are getting. So let's say we have some mu. Now what does it say? So if the noise is less, you are in a particular ith channel, you are going to allocate more power, whereas for the channels which have higher noise, you are going to allocate less power. So that's what this optimal policy is saying. Now this can be visualized in this fashion. So let's say on the x axis I am plotting these key channels. So I have this channel 1, channel 2, channel 3, like that I am plotting, and here I am plotting power. So initially I plot the noise power. So if you see this level high, it means the noise level is higher. So noise level of N1 is more than N2, but it is less than noise in the channel 3. So that's what this height of this N1, N2, N3 means. Now the power allocation strategy that I derived tells me that I should first add power, to this channel. Okay, first add power to this channel, then I should start filling power to this, giving power to this channel, and this is my mu, then this channel would not get any power. So as I said, the vertical level indicate the noise levels in various parallel channel, and as the power is increased from 0, we start allocating power to the channels with lowest noise. As I just showed you, I am first going to pour power into this channel number 2 until I reach this level of, and then I start pouring power in both of these channels. Okay. Now the process of allocating power to various channels is similar to the way you will pour water in a vessel. Let's say you have a bucket and I put some things in the bucket. So some items which are tall, some items which are smaller, and I start pouring water into this bucket. So how will water get filled? So first it will start filling over the items which are small, right? Start filling them, and subsequently start filling water on the items which are tall. So this is precisely the way this power allocation strategy is happening. You can think of those items I put in the bucket as noise level. So I will start, once I start allocating power, I will give power to those channels which have less noise until power plus noise becomes equal to noise of some other channel, and then that channel will also start getting some power. So you can see here from this example, if my nu was this, then my power allocation strategy would have been, I would have allocated power P1 here, which is less than the power I allocated to channel 2, which is P2, and I am not allocating any power to channel 3. So this is known as water filling. This way of power allocation is known as water filling, because this is precisely the way water would fill if you have things kept in a bucket of various heights. Okay. So we just talked about parallel Gaussian channel where noise was independent. So noise at channel 1, noise at channel 2, those were all independent. Now what happened if the noise are not independent? That is the case corresponding to colored Gaussian noise. So now we are considering that noise is not independent across the channels. So let K of Z be the covariance matrix of the noise, and let K of X be the input covariance matrix. Now we can write the power constraint on the input like this, which can be equivalently written in terms of trace of this covariance matrix on the input covariance matrix K of X. So this can be written as the trace of 1 by n times trace of input covariance matrix, that is less than equal to P. Now here the power allocation depends on n, so we have to calculate capacity for each n. So this is similar to the case of independent channel. If you recall, the mutual information between x1, x2, x3, xn and y1, y2, yn can be written as differential entropy of y1, y2, y3, yn minus differential entropy of y1, y2, yn given x1, x2, x3, xn. And what are these yi's? Yi's are xi plus zi. And since input xi's are independent of zi, we can write that differential entropy of x1, y1, y2, y3, yn given x1, x2, x3, xn as differential entropy of z1, z2, z3, zn. However, there is one difference from what we had earlier. Since earlier the noise was independent, we could just write this as summation of differential entropy of zi, which we cannot do because now we have colored noise. Now this differential entropy of z1, z2, z3, zn is determined by the distribution of noise, and it does not depend on input distribution. So to maximize this capacity, we need to concentrate on this term, joint entropy of y1, y2, y3, yn. So as I said, maximizing capacity is basically we have to find out what is the maximum value of this differential entropy, joint differential entropy H of y1, y2, y3, yn. Now we know that entropy is maximized when y is normal distributed. So for y to be normal distributed, because z is normal distributed, x also has to be normal distributed. Sum of two Gaussian random distributed variable is also a normal distributed random variable. So the entropy is maximized when y is normal distributed, which is achieved when input is also normal distributed. Now since input and noise are independent, so the covariance of the output, which we write as denoted by k of y, is equal to k of x, which is the covariance of the input, plus covariance of the noise, which is k of z. So differential entropy of y1, y2, y3, yn can be written as half log of 2 pi e raised to power n, and determinant of this covariance matrix of the input plus covariance matrix of the noise. So the problem of maximizes this then reduces to choosing our input covariance matrix Kz such that this determinant is maximized, subject to the input power constraint which we wrote in terms of condition on trace of this input covariance matrix. Now we can decompose this covariance matrix Kz into Q diagonal matrix and Q transpose, where Q transpose is an identity. So if we do that, we can write this determinant of Kz plus Kx as Kx plus, this is a decomposition of this matrix K of Z, and after we do simple matrix manipulation, we can show that this can be written as determinant of matrix A plus some diagonal matrix lambda, where this matrix A is given by Q transpose covariance matrix of the input times Q. Now we are going to make use of a property of matrix which says if we have any matrix B and C, trace of this matrix B and C is same as trace of the matrix CB. So we can write the trace of matrix A as trace of matrix Q transpose KXQ, which we can write as trace of Q transpose KX. Now this is an identity matrix, so then trace of A is nothing but trace of this input covariance matrix K of X. So then the problem reduces to, so the maximizing this determinant of A plus lambda subject to this trace constraint, where the trace of A is less than equal to n times P. Now to solve this, we are going to take help of Hadamard inequality. Now recall in the lecture for differential entropy we have proved this Hadamard inequality. So Hadamard inequality states that determinant of any positive definite matrix K is less than the product of its diagonal elements. So this determinant of K is less than equal to summation is product of these diagonal elements, with equality happening only if the matrix is diagonal. So then determinant of this matrix A plus lambda is going to be less than product of the diagonal elements of this matrix, and this will happen with equality only if this matrix A is also a diagonal matrix. Now since A is subject to this trace constraint given by this and AI has to be greater than equal to 0, then the maximum value of this product of these diagonal elements is obtained when this is equal to some quantity mu. However, AIs cannot be negative, so it may not be always possible to satisfy this constraint on AIs. So in such case we show by standard Kuhn-Tucker conditions that the optimal solutions corresponds to basically this, where we choose this water level mu such that summation of AIs is equal to n times P. So this is similar to basically water filling in the spectral domain. So the value of A that maximizes the entropy is basically given by this, and this will in turn, because this value of A will maximize differential entropy of y1, y2, y3, yn, This in turn will also maximize the mutual information. So this is how you are going to do the power allocation in case of Gaussian channel with colored noise. So with this we are going to conclude our discussion on parallel Gaussian channel. Thank you.